Okay, so what we can do now, I mean, you have this now, and you can say, okay, is this the size of this scratch? Is this enough for me? Is this too big or is this too small? Then you can adjust the force to have it bigger, smaller, or whatever you want. Okay, so I mean, what we can do, maybe we can measure this to see, okay, I go to analysis, I can create a cross section and may cut it like this, okay? And then I have the line in the back side, okay? And this is my scratch, okay? I just make cross section, and then I can measure the length. Let's say if I measure the length from here to here, let's say, and it's make me like 120 nanometer. So the hole is about. Is this one? Yeah. Wait a minute. Wait a minute. Wait a minute. I will make. Wait a minute. Yeah, yeah. Just okay. I will just make this small, and then I make this a little bit big, so I see exactly when I make a cut. Let's say create cross section. Then here, when I make this, so this is here. The up is up. Then the lower part. Okay. Okay. So this, I mean, it's more up in this side, and then this is the hole, and this is the material around. I take this one. Then, I mean, this is the material outside, inside, and outside. Okay, and this is, let's say, the depth. I mean, let's say from here to here. I mean, no, this is, let's say, the depth of my hole. It's about, let's say, 80 nanometer. So this is 80. This is, let's say, I make 80 nanometer holes, and then the material outside. This is from this side and from that side. So in total, with the material,
The volume up is much greater than volume down.
yeah, I mean, in total, including the material, is like 250 nanometers. Total. I mean, when you scratch 80, then you move around, let's say, material like that. And then if you look for the depth, maybe we can measure. I'm not sure how much we go down, but this is like 40 nanometers in the material. Okay? 40 in the material, in that example. So.
But we have up more than 40.
Yeah, I mean, yeah, because I mean here, I don't know how much you remove. I mean here we have like 80. Okay, so I mean this is, I cannot, I mean it depends how the tip act with the material.
عايز brittle material عشان.
Okay, so what I will do now, we can go again to the lithography. I mean, I will make a load, sorry. No, it's not a big deal, really. No, no, I mean, this is not a big problem. I mean, this is the image, I mean, okay? Yeah, but I think that was unlocked here. Okay, now what we can do, we can import what we draw. Okay, and then we can make, I mean, if you think, okay, this force is good for me, we can use it. If you need, let's say, lower force, we can make it lower. We need higher force, we can keep it higher. I mean, if you want, we can stay with this now. This is okay, this is okay. Then, I mean, حفرت. حفر ايه.
بس عايز اتاكد من حاجه.
دبل كليك.
لا مفيش كليكين.
Okay. So.
اصل انا عايز افهم لير زياده ازاي.
هلا
هي مش باينه. كوبي كده كوبي. اعمل كوبي ممكن يعمل واحده كده.
لود انا اشوف.
لود لير.
No.
لود لير كوبي كده كوبي.
لا عشان انا ما عنديش الادفانس بالهون، مش عارف ليه مش عم يشتغل.
المفروض كان يبقى في نيو كده.
لازم
يعمل كوبي، بس ممكن يعمل واحده ثانيه. غالبا هيعمل واحده ثانيه لو عملت كوبي.
اوكي، هلا ممكن نعمل درو. اوكي سماها لاير 0 اجين. ماشي.
هو شغال على لاير 0.
على طول لاير 0 سماها. هلا هيدا
مش راضي يحط لاير.
هلا حنعمل اوكي، حنعمل لود. اوكي حنعمل هلا امبورت. اوكي حنعمل امبورت فيكتور. هلا بتشوف. اوكي تيست اوفن. So now I open when I make import vector. So I mean the size of the image for my, let's say the one I made design is like 110 micron and the height is 80 micron, and my image now is 10 micron. So that I don't see anything inside. Okay. So what I do, I have to make a scale factor, so, and make maybe 0.1. I think you have to make it in like this. Image. Okay, more than 0.1, maybe 0.05. Then what is the image? Wait a minute. I mean, there is bugs, I think, in the software. Okay, size width. Okay, let me. It's here. Here. Is it here? This is one. This is one line, and this is a line, and this is the other one is up here. Okay, maybe. Wait, لازم صغره شوية أكتر. Okay, let me. mean layer 0. Okay, cancel. Wait a minute. هحاول نغير الكولر. Maybe put it white. No. مش واضحة كتير. خليها أحمر. أحمر ما حنشوف شيء. Black maybe. أصفر. خلاص. الخط هو اللي طول. الفرونت ده. Anyhow, okay. What we do, maybe I have to. باينة على الشاشة. Okay. Maybe. Wait a minute. I will take it again. I make it a factor of 0.01. Then it's, let's say, 2 micron and 2 micron size. I mean, we can put it.
لو شلناها نحط بقى احنا الاكس اوفست والواي. لو شيل عنها كده.
This is okay. I mean, here we can.
ممكن تكتب اعتقد ولا لا؟
I mean, this is the size, and here I want to put, let's say, the 0 means the center. Okay. اللي هو البداية خالص من تحت. Okay. لا. Wait a minute. So first here we have the size. We put 0.001. So we have it 1 micron, 1. And then this is the origin of this image here. And line is here. Yeah. Okay. You have the line. I'm not sure if I can move it. So, I mean, what I need to know, maybe I need to know the position here, and then I can move it to this area. So, I say if I make, so the position here is 3.3 micron, and Y position is 105 nanometer. Okay? And then I will go to, I will make a, wait a minute. ماشي اوكي.
دي انا بشتغل عليها. هو في حاجه بتتعمل على فكره. انت عملتها ابلاي صح؟ ابلاي ستارت.
انا حاسه عم بيعمل سكانينج.
ابلاي ستارت لا اتعمل ابلاي ستارت. بيعمل الاليمنتس.
1 second. Wait a minute. There is something here. Training time. 1 second. I don't know what's happening.
عايز تعمل ستوب من فوق.
انا مش شايف ابره ولا فاكر ابره.
Okay. Okay. Here. This is the layer. 1 micron. Okay. This is, let's say, the freehand one.
بوزيشن اهو تحت.
This one is the big one. Okay. Yeah. I mean, I will take this one. I mean, we need this one. Okay. Yeah, this one. So I take this one. So this is the 2. Then I make position is 3.4 micron. 0.4 micron, and the y position is 0. Okay. Oh, it's minus then.
اصل هو نسبة relative to it.
I mean, I want what I want to do. I want to move this, put it here. Yeah. Yeah. It will be minus here, 3.4 micron.
نجربها كده هيرجع لنص.
Okay, let me see. No, it's 3. It's so 0 is. So it's, and this position it should be 2.5, and then I will make edit. Wait a minute. I think I can take it like that. Okay. Okay. So I move it. Okay, move it with mouse. So now what I will do, I will take this layer 1, and then I will apply a force of 1 micronewtons, and then I will do it. Okay. Then I make start. So now it's moving the circle, make the circle, and then it's already done.
So you do layer by layer?
Yeah, like line, mesa line. And then, I mean, if I open this one to see the one I activated, so he takes this one, and he made it. Okay? And now I scan it again, and you will see. Oh.
I suppose the new version is easier.
Yeah, I mean, I will see what's. We have to update the software. Approach is done. We can start. If everything works as expected, so we have to see triangular shape. In principle, it should be that we should do all at the same time. Wait a minute, it should be now. It's here. Yeah.
انا شايف ده صغيره قوي صغيره قوي. لا لسه بتاع
هي
صغيره قوي. باينه اللي على اليمين باينه قوي في الامبليتيود.
لحظه على كده. Now you can see. You see? Here on the computer we see it better than the screen.
في الفيس هتبان.
Okay. You see it now maybe there? It's here. You see it was here. So I mean, you see that I mean the scratching in this direction and this direction works better than this direction. It doesn't work really perfect.
في حاجة تانية عملناها كده
Okay. I mean, this is, let's say, basic. I mean, what we can do, we can try to, let's say, for example, scratch something different, more designed, let's say. I mean, I will take, let's say, I can take here, I mean, I make load. So, okay. I have the image, and now what I will do, delete, yeah. I mean, I will delete all of this. This is plastic, CD. We can do oxidation, but you need like materials that you can. Yeah. Okay. So what I will do now, I will import maybe something different, vector. But I may, let's say, import vectors. I will go to. I have, let's say, a special design. Then I go to program. This is NanoSurf. NanoSurf software, and then you have, let's say, lithography template. You have, let's say, this logo. Okay, and then here I put, let's say, this is the image size. I mean, I make a factor of 0.1, and that is like 1.6 micron, 0.8 micron. Okay, and where is it?
كبير 1 من 10.
Where is it on the image? Okay, is it here? So this is layer 2, okay? And now what I will do, I will...
Shoot it from object.
Okay. This is the image. And then I can take it, let's say, here. Okay? And then move it to here. And then what I do, I make, let's say, okay. Then I go here. I mean, I will apply force of 1 micronewton, and then I can make it, this drawing. And then I will make start. And now you see that it's making the circle. Then it's doing up, down. You see. Then it's making the scratching. Let's say this is, let's say, it's design. I mean, you have to make this design, and then you put it. And now it's finished, and then I go to image, and I make approach and start. Because I made lift up, so when it's finished, it go up. Okay. And now I make start. And now I'm supposed to see the image somewhere here. So now we see this one here. I mean derivative here. You see this one here, and maybe now we should see it here. I mean, plastic is an easy material. So.
Yeah, but maybe XLP had nominal flow.
And this is the logo. You see it now?
The logo I can see.
And what we can, yeah, I mean, what I can do now, I can zoom in the logo to make it bigger to see it. So I may make them like this, make zoom, and then double click. Then I will zoom inside, and then you will see the logo in big. When you come in, let's say if you want to make the logo of the university at Nano, you can do also try to make, first you make the design with the GDS file, and then you import it, and then you. Or your photo? Yeah. Okay. And now, I mean, capture. And now you can make. هلا عملت لها zoom. Okay. I mean, zoom is here now. This and this, and now we start see the logo.
اللي على الشمال الكاملة موجودة.
هنا واضحة. بس توبوغرافي يعني.
كل ده مستنيين زوم.
عملنا توبوغرافي ايمج، عم نعمل سكان اجين.
هو بيعمل سكان وزوم الاثنين. الزوم عنده سكان جديد.
سكان اريا، نيو سكان اريا.
بيعمل سكان الاريا لكن ما فيش صورة نعمل لها صور جواها والكلام ده. هو صح؟
طب على ما ازاي؟
مش فاهم.
على ما نيكست ستيب ايه في البروجرام دلوقتي؟
لانش تايم.
نعم؟
لانش تايم.
ما انا عايز كده مش كده؟ لا بعد اللانش تايم بقى.
فعندنا ليكويد ميجرمنت بعد
ليكويد
وسبكتروسكوبي، هو الموست امبورتنت يعني. اوكي.
we do them in like 2 hours, 1 hour 50, 1 hour 30.
For
The liquid and
I mean, liquid is easy. Just I show you how to put liquid, put image, and we scan.
okay.
This
So
is
maybe
take 1 hour is okay. I mean, it's always we make it like contact mode or dynamic mode. And lithography is more complicated. Spectroscopy is more complicated. It's need like the same time as lithography, at least. I mean, yeah, I mean, you see it a little bit here.
and you can see it much better on the screen. Let's start. But you can see it. شايفينها؟ عادي
I mean, of course, I mean, if we apply more force, maybe we can make deeper scratch and things like that. I mean, you can see the scratch in this direction is not deep as in the right, yeah, because it depends on the tip how it's.
Sorry,
Okay.
the thickness of the line, how much?
I mean,
Order line.
I mean, I have to see. I mean, I think it should be like thickness.
I mean the width. ايوه مسافه
من هون لهون يعني.
من هون لهون.
80 لو
I mean, I just need to make like. I mean, I have to make analysis.
80 لو احنا ماشيين نفس
Fit, okay.
لو هو عمل نفس
That's it. I want to take a cross section here. This is the line, and this is the first line, like this, and this is the second line. Right, go here. This is from here to here. Let's say this is the total area is about 160 nanometers. So this is including the scratching inside and the material out. Okay.
This is plastic مش كده؟
Uh-huh.
How would you estimate the molecule size? It's in the nano range.
I mean, here it is. It is. I mean, I can make it smaller.
Of course, I know.
Yeah.
But I mean, plastic is usually big molecules.
Mm-hmm. And easy also. So.
So, how would you? I mean, I think it's few tens of nanos.
The molecule.
The molecule of plastic. Is it right? Polymer. Maybe 10 nano, maybe more, maybe less. How much? Order. تقريبا مش كده؟ ما تعرفش. امورفس بس المولكيول بتاعته قد ايه؟
يعني ممكن حاجه زي دي ان ايه مثلا.
طب الدي ان ايه 100 نانو. لا I mean what we are doing we are scratching I would say few molecules.
Yeah.
Not 100 molecules. I mean it should be like 10 or something like that.
If you say, let's say, one is 10 nanometer, for example, one molecule. If you are scratching here like 200, so maybe you are moving, let's say, maybe 20, 30, 40, I mean,
اللي هي ايه؟ ده
I mean, last kind of lithography now I will. So now there is another kind of lithography which is BMT image. Okay. So what I do, I import image. Okay. I mean, first this. I mean, let's say what you do. You may open Paint. Okay. And then you make image. Let's say maximum 100 pixels times 100 pixels. It must be, let's say, around this range, 100 pixels times 100 pixels. Let's say if you write, let's say, Yasin or something. Okay. You make it in black or white. Yasin. What is the? When ala? Okay. And now, I mean, I will go to C3 is a software here, and then I will say import image, and now is importing image, and I will go to where I put it. It was in my document, I think. Where I put it, I don't. File. It's on the desktop. Import image from desktop. Often. Okay. So now what is changed when I have, let's say, an image? So, I mean, this is, let's say, this is the size. I mean, I can make it smaller if I want 9 micron or 5 micron, whatever. Let's say, if you can make it like 5 micron, and here we make it 5 micron. And this is, let's say, origin 0, 0. What you have here, I mean, we are working in static force, okay, like now. And then here I just simplify to 2 layers. So that means for him, a black, he will apply, in this case, let's say, 100 micronewtons, and in white, he will apply nothing. I mean, I will change it. I mean, we put, let's say, 1 micronewtons, and in white, he applies 0. If I here choose, let's say, 256 layers, okay? And, I mean, what's happened now? So we have from 0, let's say, I mean, there is just 2 layers here. There. Yeah, so 0, let's say, like this, and then is that. I mean, this is maybe too much, so maybe you can make, let's say, 4 layers, okay? If I made it like that, I mean, if I click on it, you see, there is 3 layers actually with 0, because here, I mean, actually I have just 2 layers. If I use, let's say, gray colors and different gray colors, and we have different layers with different force. Okay, now I have 2 layers. So this is a black one, and you see this is let's say Yasin. I mean, now it's like pixels, and when I want to make the drawing, he will make it pixels. And I will select here. Maybe I can make it smaller if I want. I mean, okay. Maybe. I mean, I click, maybe 2. Five. Okay. And now maybe we can put it one. You already write something. One here we already write something. Okay. It's okay. Okay. Let's say put it here. Okay. Just I mean, even if we'll not scratch everywhere, but like this. Okay. And then I will make imaging, spectroscope, lithography. I have acquisition. I mean, I think that. Yeah. I mean, I need. لا ما I didn't yet start. I mean, I need first to load the image. I mean, problem imaging from here. This is not good. You know what I have to do now? I mean, I need to stop. I mean, I need to make a load. Okay. I make stop. لا خلينا نشوف هون. I make. No, I want to try. Start. Okay. You see how it's making scan? It's making point point. I mean, this you see that it will take more time because you have different points.
شايف الإبرة دي؟ شايف؟ there's no doubt يعني.
I mean, now the expectation is like 3 minutes to finish this. And I'm not sure what we will get because the other one was really scratching, and now we are just pushing. Maybe we'll, because scratching we have more for. At this point, maybe we'll not see anything. I'm not sure. Maybe we should need to apply higher force. Yeah. I mean, all the things we did with AFM was mainly, let's say, topography image. So now what we will do, we'll do spectroscopy. So that means instead of making image, we'll make just spectra. Okay, so now what I will do, I will just explain you the spectroscopy, and then I will see what we do next. So, I mean, usually as AFM, you can do more than imaging. I mean, about spectroscopy, what we do usually, we measure, let's say, a channel as a function for other channels. So let's say we fix one channel or we change voltage of one channel, for example, and then we see what's happened with the other channel. And there are different kind of modulation, I mean, and different kind of possibility to do different spectroscopy. I mean, if you look, let's say you can make the distance, let's say, for STM, you can measure, let's say, the tip as a function of voltage. I mean, you can make, like, say, IV curve. This is with STM. This you don't have, but I mean, this is something. For example, you can do also with conductive AFM, also electroforce Kelvin and piezo force. You can also do, let's say, IV curve. Then you measure, for example, you change the voltage and then you measure the current and see how it changed. And maybe we can make, let's say, electrochemical probe. I mean, what you do in this kind, let's say you have chemical on the surface and you do, let's say, chemical reaction on the surface. And with AFM, I mean, let's say with scanning thermal microscope, you make, let's say, tip heating, so we can heat with the tip. Locally with a spectrum, we make a spectroscopy. I mean, heating the surface. You can make, let's say, magnetic field, and you can make, let's say, frequency change. So this is, let's say, there is different kind of modulation of channels. I mean, in static, let's say, in contact mode, usually we have like deflection channel, let's say, and then we say, let's say, we can measure also, let's say, the friction. In dynamic mode, we have the amplitude and the phase, which is what we measure actually. In contact, we measure the deflection of the laser, and in dynamic mode, we measure the amplitude and the phase. And in STM or on conductive AFM, we measure that, so the tip current. So we measure the IV, the current, how is the current change on the surface. Let's say with Kelvin, we measure the amplitude also and phase from another logging. We will not talk about this now, okay? I mean, also, well, let's say with scanning thermal microscopy, we measure temperature. With EFM and MFM, magnetic force microscope, we measure phase. And then with piezo force microscope, we measure, let's say, height and phase. So there is different things we can do with AFM modulated to get different kind of information. I mean, the most important now, just talk about the most common and most important spectroscopy is the force as a function of distance. Or let's say deflection as a function of force. I mean, which one, which module, and which channel. So, I mean, usually we use contact mode or static mode to do the spectroscopy. I mean, the modulation channel is the distance. So we change the distance, we go up and down to see how the distance is changing. And the measure channel, we are measuring the deflection, how the deflection change on the detector. And then we get, so the distance and the detector, because the deflection is mean force, and the distance is the movement, okay? And then you can measure force as a function of distance. I mean, this is what I mentioned yesterday. So we have like the tip is in position A is far from the surface, Then when you are coming close to the surface, very close, then you have attractive force, is give B position. You press inside the surface and this is gives C position. And then when you retract, we said that it will not remove at this position because there is adhesion force. And then you have to go further. This is give D position. Then you have E position and then F position. And from this slope we said we measure here, this slope we can get the stiffness measurement, and here we can get the adhesion force measurement. Okay? And then now we want to be sure, okay, how we can get like the deflection correctly. Because I mean, when the cantilever is deflecting, but say 1 nanonewton, we want to be sure this is, well, let's say 1 nanometer, sorry. This we want to be sure that is really 1 nanometer, okay? And so what we do, we usually convert, let's say, the photodiode signal, let's say, into metric deflection. So that means when it's changing in volt on the photodetector, then we can measure exactly how much is this in nanometers or micrometers, okay? And I mean, there is a law, so we use, let's say, Hooke's law, and then we can make, let's say, the conversion from volt to meters. Okay, so if you have here, let's say, you have a laser, you are on the surface, and this is the detector. When you are pressing inside the surface, so that you have a bending of the detector. So that was here. You have movement of the detector to another place, okay? And then this gives usually a slope here. And this slope you can measure, I mean, actually give this is the position of the laser. And this, let's say, what we can call it, let's say, sensitivity. And this is usually we measured in nanometer per volt, okay? I mean, this is just too general to show you, I mean, how it really, we explain it. I mean, when the tip is moving, so that we can calibrate the piezo movement. I mean, and then we can really find. So according to force is equal the spring constant times distance. I mean, the distance, we measure it from here. So we know what is the distance. We know the spring constant of the cantilever, then we can determine the force. Okay? And now, how we determine the spring constant? Usually, the spring constant is, let's say, written on the box, but this is, let's say, a theoretical value of the spring constant. If you want to know the exact value of the spring constant, there is options with advanced spectroscopy software. I will show you this, how we can do that. Okay? Actually, I mean, I will not really enter in the detail. This is, I mean, there is a theory behind this, how we can do that. I mean, and I mean, then how you can make it. You can maybe look to this later. And then, in the software, I mean, what I want to tell, we can use, let's say, Newton based on spring constant, or let's say we can use Newton based on cantilever spring constant. So we can say, okay, we know what is the spring constant of the cantilever converted to Newton because we know what is the distance and we can convert it. And I mean, there is two kinds of spectroscopy. We have the standard spectroscopy and we have the advanced spectroscopy. I mean, the standard spectroscopy, we can make like a modulation on, I mean, for a fixed range and let's say a special point. So that means we have distance. We can say, okay, go, let's say, make an offset of, let's say, 600, for example, 500 nanometer minus, and then go down, let's say, 500 nanometers. This is the fixed distance. While in the advanced spectroscopy, we can say, okay, when you reach, let's say, a value of maybe 1 in Newton, stop. Because this is usually when they want to do some kind of spectroscopy, they want to know the exact force reached, not the distance. And with the advanced spectroscopy, we can do that. And we can make, let's say, what we call it also force mapping. So that means we can make, instead of making, let's say, with standard, we can make, let's say, 64 point, while with advanced spectroscopy, we can go up to 4,000 point within one image, if we make that. And then with the advanced spectroscopy, for example, when we touch the surface, we can make stop. And then we can measure, let's say, if there is an elastic deformation over time. For example, you press like this, and then we see what's happened. Does we have something change in the material over time, or is it still fixed? I mean, then you can make, let's say, elastic deformation of the material. Or we can measure it with the AFM. I mean, this is, let's say, what we'll do. So we go to spectroscopy, then we can see, okay, we have a grid here, and then we can make a grid position, then we can select number of points inside the grid, and then we make the spectroscopy, okay? And then if you look to that, this is the comparison between two kinds of spectroscopy, the standard spectroscopy and the advanced spectroscopy. In standard spectroscopy, the tip is in touch with the surface, and then it's go up, and then it's go down, okay? While in the advanced spectroscopy, the tip is not in touch with the surface. So the tip is far, it touches the surface, and it go up. I mean, the advantage of this is that you can reduce the interaction. And then, let's say, in the advanced spectroscopy, the tip, let's say if you have different points we want to measure. So we measure the first point, it's go up, it is in air, and then it's go down to the second point. And then it's third one. While in the standard spectroscopy, the tip is in touch, it moves while it's in contact with the surface to the second point and go up, down. I mean, so usually, let's say for bio, you need to go with this mode because this is much important and less interaction and get better value. I mean, there is two different parameters to do with the spectroscopy. And I mean, there is, let's say, wizard to help you how to do spectroscopy. Just you can click to spectroscopy, you can click on spectroscopy parameter, and then he can show you spectroscopy, and then you can do spectroscopy wizards that, let's say, help to make it easier. And then you can make, let's say, this is, like, say, grid of spectroscopy, and then here you have, like, say, this is one spectra, and here you can have, let's say, this is like a map of the spectroscopy. And after that, you can export this to another software and maybe also to Excel or to Origin or any kind of software. You can analyze this data. Or there is also special software that they can click, and they make also automatic calculation of all the parameters. Yeah. I mean, stiffness is give you, let's say, elasticity information about the material. We can use, let's say, adhesion force. We can make, let's say, let's say, molecular interaction. And they can measure also. This is, let's say, this is something about single cell spectroscopy. So you can go to the surface, touch a molecule, for example, and you can take it out, and then you can measure how it changed on the surface. This is what I showed you yesterday. So we have, let's say, the force as a function of distance, and actually, if the sample is soft, the slope is going like this, and when the sample is hard, it's going, let's say, straight to 90 degrees. This is, let's say, the maximum value it can reach. Okay? And let's say, in this case, you have hard sample, and in that case, you have, let's say, soft material. And then you can measure, let's say, the slope here, and then you can, when you can measure the slope, you can also calculate the stiffness out of it. Okay? This is what I showed you yesterday. I mean, this is about, they make stiffness measurement, and they make, let's say, histogram, and then they compare the results to see what they got. And then this is what we saw yesterday. If you have, let's say, cancer and non-cancer cell, and then you can see there is difference in stiffness. Yeah. And also, I mean, we can get also, let's say, indentation module. So when you have the spectra here, you can measure the indentation depths. I mean, how much you indent in the material. And this is maybe we can talk later about that. Okay. Yeah. And this is, let's say, I would say this is a basic spectroscopy. So now we can show something, and then when you measure, you will understand it better. Okay. And then at the end, let's say when you have like spectroscopy like that, you can, each point of this is give you, let's say, a spectra here, and then you can make, let's say, histogram out of this. For example, if you want to measure, let's say, the adhesion force or the slope, and then you can make comparison between different materials. And this is, I mean, very useful if you want to do, let's say, stiffness or something on polymers. This is something you can really do it very well with the system. So now I will go to the software, and first of all, what I want to do is I want to make spectroscopy force as a function of distance, let's say deflection as a function of distance. For this, I will use contact mode, because we said that is in contact mode we measure the force as a function of distance. And also we use contact mode because the tip is, let's say, I mean, the spring constant of the tip is very low. Let's say 0.1, 0.2 Newton per meter, and any kind of deflection, it can vary, any kind of force, it can very fast make a deflection. And then can sense it. I mean, with the advanced spectroscopy, we have first here a button called thermal tuning. When you make this, click on this thermal tuning, I mean, let's say, of course, first we select is a static force, and then we select contact, for example, and then we go to thermal tuning. And this thermal tuning, actually what it's do is measuring the tip in air without any excitation. It's just making how to see how is the thermal, how it's moving the tip, and how it's on the detector. And then you make Fourier transfer on this, and then you find, let's say, maximum peak. If I make just, I click start, I don't need to do anything. Just you click start, and then, I mean, auto scale here. Then you see there is a peak here. So the blue one is the average, and the other one is, let's say, the real time, in real time. And when you make a comparison here, so I mean, what you can do, we can maybe, this is, let's say, the area where he's making the fit, okay? And this is the area. I mean, I can make it smaller. Okay. You see, this is the peak I want to he find. It's around, let's say, 12 or 13 kilohertz, which is expected to be around this for this cantilever. And then what I do, I mean, I said this is maybe too much. I can change the range here. So I said, let's say, the peak fit minimum is 7.8 kilohertz. Maybe I can put it 10. And you see, when I put it 10, then it's make it smaller. And then maybe here I can put it 15, maybe. Oh, and then the other one, maybe I can put it 12. Let's say 16, something like this. Okay, and then it's making a fit along this spectroscopy. And then what you do, so you see here, that is find a value. Okay, it's here. So it find a value of, here, the spring constant is about 0.2269 Newton per meter. Then you click stop, and then you can say, ask him, okay, use this result. So now in the AFM, he put that the spring constant of the cantilever is about 0.269 Newton per meter. I mean, if you look to the let's say the cantilever here is written 0.2, okay, but the exact value we found is 0.2927 Newton per meter. Once we have the exact value, we close this. I mean, of course, I need to put a sample, and then we have to yeah, this is what we'll do later. So just finish this, okay? And then I go to spectroscopy. Here you click on more. If you click on more, you will see that you have, let's say, a standard spectroscopy, and you also have, if you click on, you have, let's say, advanced spectroscopy, okay? So first of all, we have to put a sample, and then we can, let's say, measure on the sample. So the approach is done. Let's say if I made topography image, I may make, let's say, a gold 10. This is, let's say, the gold nanoparticles. Start.
You get value for first to start with a different value first.
Yes, yes. I will show you. I will show you. I have the image. Then I go, let's say, to spectroscopy. Maybe I can make, let's say, load. Okay, so I have the image here usually, and now I want to do spectroscopy. What I do, I mean, this, let's say we start with the basic one. So I have the offset as minus 600 nanometer. So what does it mean? If this is like 0, minus 600, I am here. Minus is mean I am far from the surface. And then I can ask him the range, how much I want to go down. Usually, if you have minus 600, you go down, let's say, around the same value or a little bit more, not 1 micron. This micron will make too much. So may go too much inside the material. Let's say, I will put here, let's say, the same value, 600, okay, nanometer, nano, and let's say you have, let's say, 1 second per line and 1,000 points for one spectra, okay? You can make 10,000, I think, with one spectra. I take, let's say, if I take 1 point, make here, let's say 1 point, and then I make start. So now you see, this is the spectroscopy here, okay? So it is exactly similar to the presentation. Okay? So here, let's say this is the one, and or let's say if you have the model I was talking about here, okay, here, okay? So it is exactly, looks similar to this one. And then, so you have this slope here, and then from this slope you can calculate the stiffness, and then you can measure, let's say, the adhesion force. I mean, here you can measure how much is the adhesion force. It's easy. You go to analysis, measure length, and then you can calculate from here to here. Let's say this is the adhesion force of the material, and this you can make it from here. Okay, and then you can see that is the length is about 44 nanonewton per meter. Okay. I mean, here is about 44 nanometer. I mean, what I have to do is to convert it to force, because I mean, I know the spring constant, and then I made it. So to do it, let's say this, I want to see it exactly as a force. I go to more, and then I can go to operating probe tip here, and then I can use let's say, use Newton based on the cantilever spring constant. So, and then the value will give me here, it should be in Newton per meter. So now it's in Newton, nanonewton, okay? So what I do, maybe I can restart again the same spectroscopy, and then you can see. Okay, so now if I want to measure this from here to here, now you see, if I go analysis, measure length, then from here to here is about 8 nanonewton. So, okay. Now, because I mean, I know the spring constant, I determine the exact value, and then you can see that this value is really the exact value of the adhesion force. Okay. This is, for example, 1. What you can do also, you can say, okay, I don't want to have a point, but I want a line. I can make like a line here, and then I measure, let's say, I defined how many points I want in the line. No, here we make like 8 spectra at different position. Okay? Or for example, I can take a grid here and say, okay, I want to have a grid. Okay. And this is, let's say, a grid of 64 points. Okay? And then can I make, let's say, a grid here, I can select, let's say, 4. And let's say this is, let's say, 4. That makes sense. And then let's say I have a grid of 16 points. And now I say, okay, make a spectroscopy of this 16 point. And just I need to click acquisition, I click start, and then now you will see that he will make 16 spectra. Okay, you see now he finished the first point, he finished the second point, the third one, so the fourth one, and then he will finish all the spectra, and then you can make, let's say, if you see if there is a difference or make an average, this is the same material to have more statistic data on the surface. I mean, you see now it's measuring the spectroscopy. Actually, this is the line here, and then this one here exactly is the slope where it's really going up here. Okay, from exactly this point here at 0. And now, I say, I finish my spectroscopy. Okay? And again, I mean, this is, let's say, the basic spectroscopy. What we can do, I mean, we can go, usually we have to go to spectroscopy wizard, make force distance curve. Wait a minute. Go here. Usually we have to make a deflection calibration. You know, when the cantilever is making deflection, we have to make deflection calibration. You just click on deflection calibration, you see, and then you don't need to do anything. You just click start deflection calibration. And then what's happened? Actually, I need to show. So now actually it's making like 5 spectroscopy here in the back side, and then it's calculating the slope. And then it can determine exactly the deflection value. And then it will find, let's say, a deflection value of, I don't know, Newton per meter. So that means how much volt per meter so it's find, let's say, the deflection now, current deflection sensitivity is 160 nanometer per volt. And what he found now, the new value is 178 nanometer per volt. And say, okay, this is, let's say, a reasonable value, okay? Then you say, okay. And then, I mean, if you look here in the more, there is, let's say, here, you see? When you go to probe, he puts the deflection 1.77, okay? And the spring constant 0.26. This is the value we found for this 2 parameter. And now let's say we calibrate the AFM for spectroscopy. So you have to do this if you want to get an exact value of spectroscopy. Then you have, let's say, the minus 600, and then we have here now is the range is 200, but let's say you can make it plus 600. So, and then if you go to the advanced here, we have different parameter for the advanced. So, I mean, this with here, I mean, you can make, let's say, this is forward modulation and this is backward modulation. I mean, if you look to the spectral we measured before, there was 2 lines, right? Maybe you should go to gallery. Here there was 2 lines. The black one is, let's say, forward, and this is backward. Okay? And now we can control the movement of the tip in one direction or in the other direction. Okay? We can control it in both directions. And what we do now, we go to more. Let's say we say it's fixed stop by value. So that means I will tell him, okay, when the tip reach a value of maybe 5 nanonewtons, stop. Because sometimes, let's say, if you're using, let's say, soft material, if you press too much, you may destroy it. So you say, okay, when I reach a force of maybe 5 nanonewton, I stop. Then you can see this is my, let's say, I have a range of 256 nanometer. I am far from the surface. Then I will go down with 1,000 point, and let's say sampling rate is 1 kilohertz, means this is the speed. If I put, let's say, 2, that means I will go just 130 nanometers with this time modulation, or maybe you can put it, let's say, 1, keep it like at default now, okay? Then when I arrive to the surface, I will say, okay, make a pause. Let's say, we can say 1 second or 0.1 second. Then he will touch the surface, he will stop for 1 second, and then continues. And then I say, okay, during this 1 second, maybe he will measure, let's say, 1,000 points, for example. Okay? And then here we say, okay, retract for the same distance, for example, and then modulation is 1 second. I take just 1,000 points maybe, and then it will stop. Okay? Because this is fixed length. For this here, fixed length, I said, okay, just go back 256 nanonewton. Okay? And while here I ask him, okay, when you reach a value of 5 nanonewton, stop. And the other, then I just go back. I can also ask him to go by force. It depends on me. This is usually how we do it. And here you can increase, let's say, the number of points, and then you can get a higher point. Let's say we can start with that. Okay? And then what we do, we can make a spectroscopy. Let's say, I keep all my value, I prepare them, and then what we do now, we can do, let's say, advanced spectroscopy. You can see here that is top value, and I can make, let's say, I make one spectra, I select matching. Then I make, let's say, one spectra in the center. Start. Okay. So actually with the AFM we have also the possibility to, let's say, in the right side here we have, let's say, monitoring. So we can really see, let's say, what's happened with the deflection, what's happened with the piezo when it's moved up, what happened with the motor, and you can monitor the signal here when you are making the measurement. So, I mean, okay. Okay, I have the image now. Okay. I want to make, let's say, a new measure. I will just take 1 point. I will go to more.
No one calculated for points.
Uh,
If I didn't choose any one,
Okay.
It would calculate for everyone, or
I mean, you have to choose whether you want to make 1 point, 10 point, 100 point, and then you give you the value.
I asked the question because the start point, the start button is active. Don't shoot.
Here? Yeah, I mean, when I click this, I'm measuring the point in the center of the image. Okay, 1 point in the center of the image. Okay? Yeah. Then I go to spectroscopy. Let's fix the formula. I mean, I'm not able to get topography image because it may telling me the approach is done. I just want to see the position of the tip. Okay. Okay. So now I'm again in touch with the surface. I go to spectroscopy. Let me see, load. I stop by H. I can make it like 5. I make start to see. Minus 500 to minus 200. Okay. So now it works. So what I did now, I said to the AFM, he will start here from, let's say, minus 200 nanometer. And if you look to the advanced spectroscopy and we compare to this result here, I say, we say, okay, start from minus 200 nanometers, and then when you reach a value of 20 nanometers, then you stop, and then you go back minus 256, and with, let's say, 1,000-point scanner, okay? So I am here, minus 200 is here, okay? This is my 200, he start like this. You see there is like small attraction first, and then it's go back until it's reached, let's say, 20 nanonewtons. Then it's go down, ask him to go down until he reached, let's say, a minus 256. I mean, it should be from here to here minus 256. Okay, because this is 0. I mean for him from this point, and then it's go back minus 200. Okay. I mean there is, let's say, an example. I mean I can send you something, let's say model as a basic. You can use this to start, let's say, the advanced spectroscopy. But the idea is that you can start from far from the surface, and then you go down and go back and go down and go back. Okay? And of course, you need some practice to see. And then what is important, you have the spectroscopy. You can measure the adhesion force. You see that it's clear, and then you can measure the slope here. Okay? Yeah. I mean, this is, let's say, spectroscopy. And in addition, at the same time, you can also, when I'm making a, let's say, we can make a grid here. I can show you. I mean, okay, say this is okay for me, this value. Then I can make a grid. You can say, okay, make me a grid here. We can say, let's say, 4 by 4. And then we have 16 points. And we will do it in, let's say, in the same way, so advanced here. And what we do now, I make set. And then if I online, and then I make start. And then you see here, this is the deflection, and then this is the piezo. You see, I'm going down, go up, go down, wait a minute. Here, let's say this is the waiting time, go up. Then this is, let's say, the waiting time. Then it's go up. Again, go down. This is what's because I asked him to wait, let's say, 1 second. Then here it's waiting 1 second, making the spectroscopy, go back, waiting, go back. And then when it's finished, the spectroscopy, for example, I can tell him maybe go back maybe half a micron or something, so you can retract. And then you see this is the position, minus 300 of my piezo. This is, let's say, minus 600. And then you see how it's moving up and down. And then this is a deflection also because it's related. And then you can see you have the spectroscopy, and then maybe sometime this is maybe short, it's not long enough. And then you see here is retracted to the minus 275. Okay? So this you can really monitor in the spectroscopy. Yeah, maybe it's a little bit difficult, but yeah. Okay. So okay, so what we'll do now, we'll do liquid measurement, okay? Maybe we can make stop because this seems too complicated. Okay. It's easy, very easy. Okay, so what I will do now, I will make home, okay? And we will change, so we put the dynamic mode cantilever. I mean, in contact mode, it will work the same way. Nothing special, so just the same parameter. But in dynamic mode, we'll change a little bit. Okay? So, I mean, now I will stop. We change it. Yeah, I mean, now what I will show you is not how to prepare the sample. I mean, show you how we put it in, let's say, in liquid media, and then you can measure in liquid. This is the idea. I mean, you can have, let's say, any kind of Petri dish or something. You put it inside liquid, and then you can put everything in liquid, and you can measure. This is not a problem. Okay? I mean, I have no Petri dish, but I have. I will show you how I will do somehow. I have, let's say, I mean, I have a pipette, and I have, let's say, special samples that I can put it in liquid and show you. But I mean, for you, you can have Petri dish. We can put everything in Petri dish. This is also fine. Okay. It's okay. This is fine. Okay. So. What we will, let's say, what we will do now, I will take standard sample. I mean, I can measure any kind of sample. Let's say we can use, let's say, graphite, or let's say we use mica. I mean, and then to this is like usually the standard sample we use in liquid. We make, let's say, if you want to measure particles in liquid or something, we drop in this material. Okay, so this sample that has the let's say the specificity. Let's say we can remove plane very easy. I mean, I don't know if you know. You just put, like, say, do you have a scotch here?
I should.
Just
Yes, I do.
okay. Well, I will take, let's say, I will show you what we do usually with this kind of material. Oh, you have this, let's say, this is mica on, actually there is Teflon around. And then when you put water, it will make like just a bubble. It will not spread out. And then, let's say, you want to clean the surface. And let's say, now we're making like more sample preparation. Okay? You clean the surface. So you take like just this one. Let's say you deposit something on the surface. Now you said, I don't want it anymore. I want to prepare a new sample. You just to put like this scotch and that, and then you make like that. And then if you see that, I remove plane. You see? So then I remove plane, and then I have now, let's say, a clean surface. Okay? And then I have the clean surface, and then I can put, let's say, new material. Let's say, if you want to deposit particles, usually, because this is, like, say, atomically flat, and if you have something like 1 or 2 angstrom, you can really see the difference on the surface. Okay? And it's another example also. I mean, usually also, let's say, you can use HOPG. I mean, also HOPG you can do more or less the same as this one. So you have, like, say, HOPG here, and again, you can scratch it the same way. Okay? But this is maybe you see it better. This one you make like that, and then also scratch it. So you see that I remove graphite. So this is a graphite plane. And I got Nobel Prize on graphene for that, just on this, you see? They just scratch these things, and then they get Nobel Prize. Okay, so. So everyone has this since a long time, but nobody studies that. Okay, so and then this you can use also some kind of. So what we do now, I will take the sample. I mean, let's say now there is nothing. This is just like a substrate. Okay, there is nothing special. But if you have something, you can see. I will take maybe the HOPG. You can see better. Okay, and then I put, let's say, this is my sample here. Okay, and now first of all, I need the special sample holder for liquid. So I mean, this is the compared to the other one is different. So this one, I mean, you see there is nothing inside, and this one you see there is like transparent film. Okay, you see there is like a plastic film, and I mean this is actually to avoid water to go inside the scanner. Okay, so I mean you see here, I mean this is, let's say, the standard. There is nothing inside, and then you see this one there is like film, transparent film. Okay, so is it clear for you? You see, so this is like there is nothing, and here there is nothing, it's empty, and this one has like transparent film. You see the films? Okay. Okay. And now what we do, we put a cantilever. So I will take dynamic cantilever. Usually you have also, for, let's say, minimum optimal result, usually use cantilever with, let's say, coated with gold, because the gold is, let's say, inert, and then in liquid does not make any effect. I mean, any reaction. Sorry, it's good, because this has aluminium, and usually aluminium they are not stable. But now for what we want to do now as a basic is okay. But if you want to work, let's say, all day in liquid, then it's better to have a cantilever with gold coated. No. Okay. I mean, first start to do these things, and then when you come to that point, you can buy it. Okay. So I will change the cantilever. So I change the cantilever. So what I do now, I may adjust the laser first, and then after that we put liquid. So we adjusting the laser, we already do it a lot of time. So I mean, now I will adjust the laser. So okay. So, I mean, here you see that, I mean, you still see a little bit more laser because you have, like, say, transparent film on the sample, and you always still see a little bit laser. But you see, if I make it complete, you see the complete laser, okay? And then here, yeah, out, I am on the counter, okay? So, I adjusted. Now, I adjust the laser on the detector. Okay, so laser is adjusted more or less on the detector. Okay, and now I put my sample and then we can measure. So, I mean, if you look again to this cantilever, I mean, I don't know if you see it, but there is like small bubble on the cantilever. You see there is small bubble? Actually, and this what is alignment structure. So that means when you are in liquid, the laser is going perpendicular. And when it's coming perpendicular to, let's say, from air to liquid, it will reflect it perpendicular. Okay? So that means when you go to liquid, you don't need to adjust the laser. Because with other AFM, you need to adjust the laser sometime in liquid, and you cannot see anything, and then it's complicated. Okay? So that you have, let's say, you see there is small bubble here. And this is actually alignment structure. So when the laser comes, it will go perpendicular to the liquid, and then you don't need to adjust the laser. Okay? Because, I mean, you know, in reflected from air to water, you have the normal is always reflected in the same direction. While if you have an angle, it's different. So I put the cantilever, and now, I mean, maybe I can show it on. Okay. So I put like here, and now either you have, let's say, your sample on a petri dish, which is full water. I mean, of course, the water should not, when you approach, should not be higher than this quantity. Otherwise, the AFM will touch the water, and there is electrical connection. Okay? So you have to be careful about, let's say, 6 millimeter water. I mean, it can be big like this, and maybe 6 millimeter maximum. And now, for my sample, I will take water. لا خليهم ما مشكل بس
طب ايه رايك لما نحط هنا كده؟ المساحه دي تنفع؟
I mean, you can also work not just in water. For example, if you have acid or basic, you can work on it. But after that, you have to clean this. You clean it after. When you finish measuring, you immediately clean it with, I don't know what, water or something else, and dry it. Okay? Okay.
ماشي اعمل ايه؟
Okay. Just I clean it a little bit. Okay. Okay, this water is for me is okay.
اشربها.
تشربها بعد شوية. Okay. So what I do, I have like say a pipette, okay, and you can, I mean, I take. Is it broken, mine? I think it's already. It's, I mean, I see it's broken here.
broken.
Okay. I mean, yeah, I take water, okay? I take again. So what I do now, I put like, let's say, water like here, okay? Like, that's it, you see? One droplet of water, okay? I mean, this is, I mean, now. I mean, we can have Petri dish, we can put a full water of it, you see? I mean, if I rotate it like this, you see? It doesn't drop, okay? Because it's just one droplet of liquid, okay? It is water, so one droplet of water. If you put too much more, of course, it will go out. Yeah. Okay? So, this is, yeah, you see? Okay? Okay, it's already it's clean. Okay, now for now. But I mean, if you work in real clean, then you need everything to be perfect. Okay, and now I will take another one here. I mean, I can put also something like that. Okay, also a drop of water. Okay, and now I have my water. Another step, what I do, I will put also water on this one. Okay, because now I have, let's say, a limited quantity of water. There is not too much. And now I put usually here, like also a droplet of water. Okay? So, I see there is water. You see it? And of course, you see there is water. I mean, let's say also a droplet of water. And then what I do, I will approach to the other droplet to this one, and they will touch each other. Because then the cantilever is in liquid, and the sample is in liquid. So everything is in liquid. Okay? That is the idea. And I mean, if you have, I mean, I don't know, Petri dish with full liquid, you can just immediately put it inside. Okay? Mm-hmm. Like this one, for example, we can put it immediately inside. And okay. And
How much time is left for liquid only?
5-10 minutes, yeah, maximum. I mean, now just I want to make the approach and start scanning. I mean, this is a little slight difference you will see, but just in the frequency, and that's all. Okay? Yeah, it's okay, no problem. This is okay. It's not a problem, okay? Not a problem. And now what I will do, I will put my sample, and I mean, maybe you can see, I mean, when you put two droplets of liquid, when you come together, will stick together. And this you can, if somebody wants, you can see from this side. I mean, there is no camera to see, but if you look from that side, you will see it. You can come from here and see. I mean, I have my sample here. Let's say, I mean, maybe the height isn't, I mean, first I have to go up.
Yes.
Okay? Now I go up already. And when I go here, under the liquid, you see, okay, I will go under my Okay, I will go. Maybe there is too much water. Okay. Okay, and look now. Boom. You see?
Yes.
See how it's happened?
Yes.
Okay. Okay.
الوتر ما بينهم.
Okay, there is water between sample and. I mean, you can come and have a look. You see, there's really water films. You can look from the side.
الاثنين بقوا ملتزقين هو ده اللاينمنت بتاعي كده.
This is I mean, now sample and tip is in liquid. And now what I do, I made the approach. Okay? So. Okay. I mean, if you want to see now, look to the side view. طلع بالسايد فيو. شايف؟ وشايف الخيال؟ بعيد. Okay. Okay. So in liquid also we have, let's say, we can see also the tip and the sample, here, like 45 degrees. شايفة؟ Here. Like this. شايفة؟ هون. اعملي 45 degrees. إبرة. اوكي؟ وفي الخيال تبعها تحت داون. شايف الخيال؟ اوكي؟ دي الإبرة فوق والخيال تحت. اوكي؟ No, you feel small. What do you want? You want to examine powder? No, it's not like this. No. You take, let's say, powder in solution. Then you make a drop on the liquid, on the sample. This, let's say, this one. And then you let it maybe dry, and then you can measure it in liquid after that. Okay? Then you can, but you have to let it, I mean, the particles need to stick on the surface. Okay? And to stick in the surface, there is two ways of doing this. Either you put it and let it dry, or you put in the solution just, let's say, particle solution, and usually you have, let's say, the surface sometimes is charged. You make, let's say, you use what we call buffer solution. I mean, I can explain you later what is this. Let's say, contain salt or magnesium or something to make the surface neutral. And then the particles will stick to the surface. If you may say, let's say, if you don't want like your particle dry in air. And then when you put, then stick in the surface, and then you can add liquid, rinse it inside liquid. So you put, let's say, some water, you remove them, you add new water, and then you remove all particles and just some particles stick on the surface. Okay? This is something we can explain later how to prepare. This is sample preparation. Okay?
is دي important اللي هي الوتر اللي بره على الطرف حالات اللي على الطرف الوتر دي
لا ولا شيء لا ده ليش التجربة. اوكي
ما يجيش
مش هتشوفها للنور المية ضرب فيها الليزر
مش هشوفها صح؟
مش هتشوف شيء. بطلع من هون شوف عارف تشوف هون زوم inside this.
كده؟
بالهول. Can you focus?
فوكس.
ما بين شيء ما حيبان.
بنش.
Okay. Okay. So now, usually if you want to work in liquid, you can use, let's say, any kind of tissue, put it in water, and put it inside. And then so that the water on the sample will not evaporate very fast. Okay? So you can put inside, close here, water on some tissues, and they have humidity, better humidity. Okay? And now, so what I do, I will go to liquid, okay? And now we will go to phase contrast. I will use, let's say it's tape 190. And now what I want to do, I will make frequency sweep. And when I do frequency sweep, you will see that it's different now. So, wait a minute. I mean, here I have to put it. I will try 2000. I mean, usually, okay. Okay. So in liquid, what's happened? Usually, let's say in air, you see that there is also a sharp peak all the time. While in liquid, because you make oscillation, so you have also the perturbation of liquid. And usually, you don't see really a clear, sharp peak. And also, the let's say the amplitude of the peak is reduced. Let's say we are working at 2000 millivolt. Maybe with the liquid, we cannot reach more than 1000 millivolt. Okay, because this is because we are in liquid. Because of the liquid, because you have viscosity liquid making affect the tip. Okay. 1000 try. Yeah, put. So you can see this is okay, and then you can say this is maybe my maximum peak. I mean, every time can give you different kind of peaks, okay? And what also happened, let's say, the frequency here is about, let's say, 77 kilohertz. And in air, it's like 150, 160. Usually it's divided by 2 or 3, the peaks, because in air it's different than in liquid. Maybe I can make it, here. I can try to make it like 1500. This is the excitation. I try to increase the excitation to increase this value here. Okay. I mean, you see that. I mean, if I put here, this is, I think, maximum is 5000. This is the maximum value. And you see with this maximum value, 5000 excitation, I reach 1400. This is the maximum amplitude I could reach. While when I was in air, here I was, let's say, 2000, and here I was like maybe 500. Okay? This is the maximum excitation I reach. I make okay. And what I will do now, I will do the approach. Then I click approach. And now he's trying to find that the vibration, excitation vibration. Then he find a peak. And he tell me, okay, this is the peak I found. Do you want to work on that position or you want something else? And we see, okay, maybe I say, okay, no, I will need to work on this peak. Or maybe on this peak. I say, okay, I can move it a little bit maybe to the left here. And then this is the value, let's say around a little bit less. You say, okay. And then it will make the approach. And now it's moving, approaching to the surface. And And when the approach is done, he will tell me approach done. So it's moving, and then we just wait, maybe. The approach is done, okay? And now I will start measuring as normal. Then here maybe I can put, let's say, 60%. I have 1.3, this is, let's say, my maximum value I could reach. I make start. Yeah, I mean, yeah, now he can finish. So now I'm measuring and we get my image.